Good day everyone and welcome to today's tutorial. So today we'll be talking about the optical instruments. So before the end of this video, make sure you like the video and subscribe to this channel to get more of the videos. Now we have different type of optical instruments. We have the microscope, we have telescope, we have the projector, and so on. There are many, but in this tutorial we'll be talking about the microscope. Now a microscope is used to view objects that are too small to be seen by the human eye. So objects that are too small, so we use the microscope to view it. So what the microscope does is that it makes the object, so that is the final image, will be really big and that it will be magnified. So under the microscope we have two types, which are the simple microscope and the compound microscope. So the simple microscope only just uses one lens. It uses one lens, and sometimes they call it the magnifying glass. Now we have what we call the angular magnification. We did linear magnification before in the previous videos. Now angular magnification is just the angle subtended when aided over angle subtended unaided. That is, when aided, when using the microscope, the angle that is subtended from between the eyes and the lens, then over angle subtended unaided. That is just the normal eye when viewing it. So we have that n is equals to beta over alpha, where beta is the angle subtended when aided and alpha is the angle subtended unaided. Now for the simple microscope, we have n is equals to minus d over f. Now this is gotten from this relation where we say the linear magnification is v over f minus 1. So we can prove this formula, but we are not going to do that now. So from this now, we have that since the final image that is produced by a microscope is virtual and magnified. So since it is virtual, our V, that's this image, is going to be minus D. And D is the least distance of distinct vision. Now we have what we call the near point and far point. Now the near point is just the least distance of distinct vision, and it is given as 25 centimeters. So the near point is 25 centimeters, and the far point is at infinity. So we use D as the least distance of distinct vision, and from this our magnification is this. Now what if because to get this magnification, the object has to be placed between the focal length and the pole of the lens, between F and the pole. But what if the image, the object is placed at the principal focus? Now when this is placed at the principal focus, the image form is at infinity. So when the image form is at infinity, our angular magnification is going to be D over F, that is D over the focal length. Now that's for the simple microscope. Now for the compound microscope uses two lenses of small focal length. So there is two lenses of very small focal length. Now this is, let's say this is where the eye to view the object Now, in viewing the object, this is where the object is placed. Let's say this is object, and we call h the height of the object. Now, rays of light will pass through this on this length, then it will come this way, then pass through the optical center and here. So where this line cross, an image will be formed, and we call it H1. So this objective lens, we have the two lenses are objective lens and eyepiece. So objective lens is the lens that is closer to the object. The lens closer to the object is called the objective lens. So this objective lens will produce an image which we call the height of the image to be H1, which is virtual. This is real, and it is what? Inverted. So this image that is produced will now serve as object to the eyepiece. So it will serve as object to the eyepiece. Then again, rays of light pass through this optical center, and so therefore the image will be produced at this place, which is H2, and it is magnified. This is where the image will be produced. Hereby, you can see how small the object is, and look at how larger it is here. Now we have the angular magnification is equal to this, where H2 is the final image, final height of image, and H is the height of the object. So when we have this, now I can do this. This is the same as this. H2 over H1 times H1 over H. If this cancels this, we go back to this. So I can do this, which is the same as this. Now from here we can see that if I'm to calculate the magnification for this objective lens, so magnification for objective lens is going to be the image produced by objective lens, which is H1 over H. So which is what we have here. Magnification of objective lens, which is H1 over H. Then for the eyepiece, if I'm to calculate the magnification, is going to be, for the eyepiece, is going to be the final image, which is H2 over this, which serves as the object to the eyepiece, which is H1. So you can see we have H1 over H. So H1 over H. So this is my objective, and this H2 over H1, which we have here, is the eyepiece. So therefore, the magnification is equal to this. Now, if we substitute this, that is, from this formula we have here, if we substitute it into this, so we are going to have, if I'm to substitute for ME using this formula, M equals to minus D over F minus 1. So for the eyepiece, since the final image is produced by the eyepiece, we are going to be having minus D over F minus 1. Then times, for the objective lens, now for the objective lens, we will not be having minus D. This D is used, that the lead distance of distant vision, is used for the final image. So an MO, which is the objective lens, is not the one producing the final image. So therefore, this, instead of D, is going to be V over F, which is focal length of the object, this is eyepiece, minus 1. So we can rewrite this, if I equate the negative, minus D over FE plus 1. That's for this. This can be written this way. So into